Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, and welcome back to Physics with Beth and Beth. I'm Beth, and today we are continuing our exploration of Unit 8 of AP Physics 1, which is on fluids. And in this video, we're going to be doing some practice applications of Archimedes Principle. If that's a new term for you, no worries, we have another video explaining the concepts of that, and it's just the video right before this one, so go ahead and give that a watch before diving in. But let's get started here. This is our first little example problem. What is the buoyancy force on a ring with a volume of 0.1 cubic meters that is fully submerged in fresh water? Well, if we look down at our handy-dandy AP Physics 1 equation sheet, we can find that the buoyancy force is equal to the density times a volume times the acceleration of gravity. Now, the tricky thing with this equation is remembering which density and which volume we're talking about. So, in this equation, we have to remember that this is the density of our fluid, and the volume is the volume of our fluid that's displaced, not the volume of our object, though in this case, since our object is fully submerged, the two are the same. So, all we have to do now that we've identified which variables we're talking about is plug them into our little equation. Just plug and chug. So, I meant to drop that. We have our density. Well, we're talking about the density of our fluid, and our fluid is fresh water. So fresh water has a density of 1,000 kilograms per cubic meter, so we can just plug that in there. Then we know the volume of our displaced fluid, since we're fully submerged, is just the same as the volume of our ring. So that's just 0.1 cubic meters. Then we multiply that by our acceleration of gravity, which is just 9.81 meters per second squared. I multiply all of those things together, and we end up finding that our answer is 981 newtons. And that is the magnitude of the buoyancy force acting on our ring. That wasn't too bad or too complicated, just a little plug and chug. But the tricky thing on problems like this is remembering what your density is and what your volume is, because on the AP Physics equation sheet, they don't tell you. So don't be fooled and remember to keep that straight, okay? All right, now let's go into a slightly more involved problem. We have a fisherman who's lowering a 5 kilogram anchor on a rope until it is fully submerged, 4.5 meters below the lake's surface, and then holds the anchor there. What is the tension in the rope? Then we're also given the volume of our anchor, which is 0.002 cubic meters. So I have room to work out this problem. I'm going to erase all this up here. All right, well, first of all, the tempting thing here is to say, well, if my object isn't moving, I have the force of gravity pulling downward, like so. And then I know I have the force of tension pulling upward, which is opposing gravity, so the two are equal, and then you go on your merry way. But wait, there's more. Our object isn't just hanging from a rope, it's hanging from the rope in the water. If you've ever held something heavy on a string, like a small anchor for a fishing boat, it's harder to hold in air than it is if you drop it over the side of your boat and hold it still. That's because you have the buoyancy force of the fluid pushing back up against the object that's helping you out a bit. So not only do we have the force of tension pulling up on our object here, we also have the buoyancy force pulling up. So our free body diagram should look a little something like this. Now we can lean on Newton's second law. We know that our net force is equal to our mass times our acceleration. But our acceleration, well, our object is being held still, so it's not accelerating, its acceleration is 0. So that means this is equal to 0. And now we can just add all of our forces up together. So our net force should have a sum of 0. Let's add these together. We know that our buoyancy force plus our tension minus the force of gravity, because that's acting in the opposite direction, is equal to 0. We're trying to solve for the tension in our rope, so I'm just going to rearrange these things here. I'm going to subtract the buoyancy force from both sides and add the force of gravity to both sides. So we know that the force of tension is equal to the negative of the buoyancy force plus the force of gravity. All right? Well, force of gravity, that's just F equals mg, right? So here, I'm going to do these off to the side. The force of gravity on our anchor, that's just the mass of our anchor times gravity. And we know our mass is 5 kilograms. and gravity is just 9.81 meters per second squared. All right, so we can just plug that into our calculator, and we end up finding that this is 49.05 newtons is our weight. Now, let's just worry about the buoyancy force here. So we have the buoyancy force. We know that that is equal to the density of our fluid times the volume that is displaced times the acceleration of gravity. The density of our fluid, well, this is a lake, so it's fresh water, so that is 1,000 kilograms per cubic meter. Our volume that's of our fluid that's displaced, because we're fully submerged, that is equal to the volume of our object, so that's 0.002 cubic meters. And then our acceleration of gravity is thankfully still 9.81. That has not changed. So when we plug this into our little calculator, we can end up finding that the buoyancy force is 19.62 newtons. So our force of tension is equal to the force of gravity minus the buoyancy force. Here, I'm going to rearrange that so that's a little more clear. So that's going to be 49.05 newtons minus 19.62 newtons. And then we solve for the force of tension, and that ends up giving us 29.4 newtons. And that is our answer. So the first step that we did, as should often be your first step whenever you have problems like this, we drew a free body diagram. We identified that we had a net force equal to 0, so we were able to set the sum of our forces to 0 because we had no acceleration. We rearranged that equation to solve for tension, and then just plug and chug with the equations that we know to solve for those other forces. And then we were home free. All right, if you guys have any questions about that problem, please feel free to let us know in the comments, and we will do everything we can to answer those for you. But for now, let's move on to our last problem of the day. So for this problem, we're going to have a boat that is floating in a lake. Let me erase all this here so I have room. Let's see, we have a boat floating on a lake with a mass of 1,700 kilograms. We also know that the bottom area of the boat is 4.5 meters squared. Now, what we're going to try and find in this problem is how much of our boat is submerged. All right, this is a tricky one because we're only given two little pieces of information, a mass and an area. We're not given a volume. Thankfully, though, if we think about how shapes are, so I'm going to say that our boat is shaped like this. Anytime you have a three-dimensional prism like this, you can always find the volume. I'm going to give it a little sail because that's cute. We can always find the volume of something by taking the area of the base times its depth. Now that is a handy-dandy little fact that we're going to be using in this problem here. So our first thing to remember, let's draw a little picture, a little free body diagram. That's always a great step when you're given a bunch of word soup like this problem. We know we have the force of gravity pulling downward, and since it's floating on the lake and not sinking, otherwise it wouldn't be a very good boat, is the buoyancy force pushing upward. We know that since our boat is stationary or at least it's not sinking, it's floating on top of the surface, that our net force in the y direction has to be equal to 0 because we don't have any acceleration downwards or upwards, right? So this is equal to 0. This is equal to the buoyancy force minus the force of gravity. We can rearrange this equation and end up finding that the buoyancy force is equal to the force of gravity. They're just in opposite directions, but their magnitudes are the same. Now, we know that the force of gravity, you guys are old hats at finding this one, that's not too bad. That's just the mass of our boat. I wrote bat. This is not a bat, this is a boat, times the acceleration of gravity is our force of gravity. And then we know that our buoyancy force is equal to the density of our fluid times the volume of our fluid displaced times the acceleration of gravity. All right, I'm going to rearrange this equation a little bit. This is the density of H2O. This is the volume displaced. Since I have a g on both sides, I'm just going to divide both sides by the acceleration of gravity and cancel that out. And then I'm going to divide both sides by my density so that I'm left with just my volume of my displaced water on one side. So let's see, where should I write this? Let's go up here. We know that the volume of my displaced water has to be equal to the mass of my boat divided by the density of water. Okay, now from earlier, this is the trickiest step, is remembering that we can find the volume of our displaced fluid by taking the area of the base of our boat and multiplying it by the depth that we're displaced. So oftentimes whenever you're finding like the volume of a rectangular prism, that's length times width times height. It's the area of your base times your height, right? The same idea applies here, but if we're trying to find only the volume that's below the surface, instead of multiplying by the overall height of our shape, we're multiplying by the depth below the surface, and that will give us the volume of displaced fluid. So our area of our base times our depth that we're displaced is equal to the mass of our boat divided by the density of water. I'm going to now know, well, we're trying to find the depth that our boat is submerged up to. This is the big thing that we are looking for. So I'm going to isolate it by dividing both sides by the area of my base. So we end up finding that our depth is equal to the mass of our boat divided by our density of water times the area of the bottom of our boat. Now I'm just going to plug in the values that we have for each of these things. The mass of our boat is equal to, let me just crouch down here, 1,700 kilograms. We're given that in our problem. The density of water is 1,000 kilograms per cubic meter. And the area of the bottom of our boat is 4.5 meters squared. So if I multiply all of those things together and plug it into my calculator, we end up finding that our depth is equal to 0.378 meters. So if our boat weighs that much and has that large of an area, it will be submerged 1/3 of a meter below the water surface. And there we go. So to recap everything that we did, we were given this problem. We're trying to find how much of our boat is submerged. So we had to remember that we can calculate the volume of our submerged boat by taking the area of its base and multiplying it by its depth. We set up a free body diagram. We knew that since our net force had to be equal to 0, since our boat is at rest, at least in the y direction, that the magnitude of our buoyant force had to be equal to the force of our gravity. Then we just plugged in the expressions that we knew for the buoyancy force and the force of gravity, simplified it a little bit, and ended up with the volume of our displaced fluid is equal to the mass of our boat divided by the density of our water. Then we remembered that fact from earlier, where it's the area of our base times the depth to find this volume, rearranged for depth, and then plugged and chugged. All right, guys, that's all we have time for today. Thank you so much for sticking with me through all of that. If there's anything that didn't make sense or that you have any questions about, please feel free to let us know in the comments and we will get back to you as soon as you can. Thank you so much for going through all of this with me and for joining me on our little physics journey today. Y'all are troopers, and happy physicsing.